In your brain, there are neurons. These neurons contain axons, which transport electrical signals from the cell body of one neuron to the cell body of another. This process needs to happen very fast, or else the signal will get lost. Different properties of these axons make sure that this is possible. All axons contain voltage-gated sodium channels, a point in the axon where an action potential, or electrical signal, can be generated. In a typical axon, there are millions of these sodium channels that open and close at different times to pass the signal from one end of the axon to the other. When one channel opens, sodium flows in and depolarizes the cell, and the signal travels passively down the length of the axon. If this depolarization is strong enough, it will recruit the opening of other nearby voltage-gated sodium channels to further push the signal down the length of the axon. However, if the signal is not strong enough, these channels will not open and the signal will be lost. Let's see a demonstration to better understand this concept. Here, our friends are arranged in a line to represent a typical axon. Each person's hand represents a cluster of voltage-gated sodium channels. When there is no signal propagating down the axon, the voltage-gated sodium channels are closed, but are ready to be activated by an action potential. Let's give our axon an action potential. When we give the first person in the axon the action potential, their voltage-gated sodium channels become activated. Since our action potential is large enough and our friends are close enough together, the passive spread of depolarization is sufficient to activate the voltage-gated sodium channels on the next person in our line. They are now capable of grabbing hold of the action potential. Once the action potential is fully passed on, the sodium channels it just passed through become inactivated. They are not closed, but they are unable to generate another action potential for a while. Eventually, they will return to the closed position and can once again generate an action potential. This process continues down the axon until it reaches the end, the axon terminal. However, some special properties make it possible for certain axons to carry their signal even faster. One of these properties is diameter size. Some axons have a wider diameter than others. This increases the surface area of the axon and reduces the amount of resistance the signal faces while moving down the axon. This allows the same sized signal to move down the entire length of the axon faster than the smaller diameter axon we saw before. Another axon property that allows for faster propagation of a signal is myelin. A myelin sheath is a protein coating that wraps around the outside of certain axons. It gives them insulation to protect any signal from being lost due to leak channels. Where myelin is present, an action potential cannot be propagated. These sodium channels are effectively removed from the axon. However, the myelin also allows for the passive depolarization to spread farther down the axon than it did before. Because of this, action potential propagation down a myelinated axon is faster than an unmyelinated axon. Some special axons, like those in motor neurons, are both wide in diameter and myelinated. This allows for the fastest propagation of action potentials possible. But sometimes the signal is not strong enough to continue down the axon. The signal does not provide sufficient depolarization to recruit the opening of neighboring voltage-gated sodium channels. Propagation ceases and the signal is lost. Our brain is an amazing yet imperfect organ. The communication between neurons is a process that must happen very quickly. Some physiological properties exist to optimize this process so we can think, feel, move, and exist in real time. Pretty cool, huh?